Originally, I was going to talk a little bit about 7.7, but I'm really tired. 7.7 is just, I guess, more ways to do Riemann sums for integrals that we can't compute. 7.8, though, is improper integrals. And I don't mean the kind that you get when you don't write the notation correctly, but specifically ones that don't fit the definition of the definite integral. And there's classically basically two types of improper integrals. The first are integrals with infinite bounds. When I have something like that, I might have, an integral that goes all the way to negative infinity up to a number, or from 0 all the way up to infinity. To have a weird example, I can go from negative infinity up to 6 of r e to the r over 3 dr. I could do a bunch of work to find out what this antiderivative is. So I'll do that without the bound notation. The integral of r e to the r over 3 dr. I would have to do integration by parts for that. So I'm going to say that u equals r, which means the du is equal to dr, so that's gone. And the dv is equal to e to the r over 3 dr, which means that v should be equal to 3 times e to the r over 3. So that would be uv 3r e to the r over 3 minus the integral of v du, which is 3e to the r over 3 dr. And I can do that antiderivative. This is 3r e to the r over 3 minus 9e to the r over 3. Plus c. But the problem with these doesn't come from finding the antiderivative, it comes from trying to evaluate it at the bounds. Because from the fundamental theorem of calculus, part 2, if I find the antiderivative, then the definite integral is just the antiderivative evaluated at the upper bound minus the antiderivative at the lower bound. So this original integral should be equal to 3r e to the r over 3 minus 9e to the r over 3, evaluated from negative infinity up to 6. But it doesn't make a whole lot of sense, generally, to plug infinity into an expression. I mean, sure, if I plug in 6, I'm going to have 18e squared minus 9e squared, and then I'll have minus. But what does this mean? Negative 3 infinity e to the infinity over 3 minus. What is that? So instead what we do is we fix it up with limits, and we find out what happens to this integral as the limit goes to infinity. So I'll rewrite my integral equal to the limit as t is a popular choice of letter. T goes to minus infinity of the integral from t up to 6 of r e to the r over 3 dr. This is the same kind of step we use when we go from Riemann sums to integrals, because the integral is the infinite limit of the Riemann sum. Just like a limit to infinity is going to be the infinite limit of this smaller, finite, definite integral. So this would be equal to the limit as t goes to minus infinity of 3r e to the r over 3 minus 9 e to the r over 3 evaluated from t up to 6. And this gives me an expression that I can make sense of when I plug them in, and I'm going to be able to evaluate or do limit techniques to try to find out what this value is. So I have the limit as t goes to minus infinity. See if I can save some of my work. I have 18e squared minus 9e squared minus the quantity 3t e to the t over 3 minus 9e to the t over 3. Now, if I look at this and I think about this as t goes to infinity, or negative infinity rather, that would go to infinity. As t goes to negative infinity, e to the t is going to go to 0. So right here I have an indeterminate form inside of my limit. It makes a lot more sense now. So I have to try to evaluate this limit to find out, well, what is the solution to this indeterminate form? And I'll use limit properties to get rid of some stuff. 18 minus 9, that's 9e squared, minus the limit as t goes to minus infinity of 3t e to the t over 3 minus 9e to the t over 3. Now, I have a couple of different ways to do this problem. I could take my infinity times 0 and divide it and do L'Hopital's. See if I can find two ways to do this. Limit as t goes to infinity of 3t e to the t over 3 minus limit as t goes to infinity of 9e to the t over 3. So that one will go to 0. Versus over here, I have the limit as t goes to infinity, e to the t over 3. Actually, I've done a lot of L'Hopital problems. I'm going to have to do 3t divided by 1 over e to the t over 3. Because that's equal to the limit, that should be a minus, as t goes to minus infinity of 3t all over e to the negative t over 3. And when I do L'Hopital's on that, I'll have the limit as t goes to minus infinity of 3 divided by negative 1/3 e to the minus t over 3. This works out to be the limit as t goes to minus infinity of negative 9e to the t over 3. But we've actually already done this limit up here, so I know that this is going to be equal to 0. Another way I could have handled this, which I think ends up in me doing the exact same work, is I could have factored out this e to the t over 3 instead of distributing the limit. But that essentially gives me exactly the same problem, because I'll have 0 times a minus infinity. So we'll just proceed to do the work that we did on the left-hand side. But what does this tell me about my my integral actually. This limit here was equal to 0. So my integral was 9e squared minus the result of this limit, meaning the result of this integral is minus infinity to the 6 of re to the r over 3 dr was equal to 9e squared. Now when this happens, when I get a number out of this limit, we say it converges. If we don't get a number, if we get a limit which doesn't exist, which can happen, or if we get a limit which is infinite, then it diverges. Which is funny because this is actually how definitions in math go. So this means that the limit was infinity or simply did not exist. I should add a specific note here. Some problems are integrals from negative infinity to positive infinity. So let me add here negative infinity to positive infinity. An example of one of these kinds is actually the normal distribution from statistics. The function that we're trying to integrate, though, would be e to the negative t squared. That doesn't have an antiderivative, so we're totally out of luck dealing with that problem for this class. But I can do something different. I can do x squared e to the negative x cubed dx. Now it's tempting to rewrite this as the limit as t goes to infinity from negative t to t of x squared e to the minus x cubed dx. But that is actually improper. It's an improper use of an improper integral. We should use different letters. What this corresponds to is we should split it in the middle, take care of one infinite case, and then deal with the other infinite case separately. And the reason is, in general, we don't know that these bounds are moving off towards infinity at the same rate. We don't know anything about them, so we can't draw any conclusions about them. So what we should do is make two limits. This is the limit as t goes to infinity of the limit as r goes to minus infinity of the integral from r to t x squared e to the minus x cubed dx. Which looks kind of scary, but the thing about limits is they can kind of swap orders without a big deal. So having a limit inside of a limit doesn't really change much as far as our work. So I'm just going to do this integral. Looks like I'm going to need a u substitution. U equals negative x cubed, so du equals negative 3x. So I'll have the limit as t goes to infinity and the limit as r goes to minus infinity of the integral. I'm going to change my bounds. This is negative r cubed up to a negative t cubed. And I'm integrating e to the u du. Nope. Du over negative 3. This is equal to, the negative 3 can actually come all the way out here because of limit and integral properties. But the antiderivative of e to the u is just e to the u. So this is e to the u from negative r cubed up to negative t cubed. So I have here e to the minus t cubed minus e to the minus r cubed. And you might be able to guess what I'm going to do next. The limits will actually distribute across these, but anything that doesn't apply just kind of passes through. So of negative 1/3, the limit as t goes to infinity of e to the minus t cubed. There aren't any r's on it, so that limit doesn't affect this part. Minus the limit as r goes to minus infinity of e to the minus r cubed. And t isn't in this part, so that limit doesn't affect that term. So as t goes to infinity, this goes to e to the negative infinity, so this one is equal to 0. And over here, as r goes to minus infinity, r cubed goes to minus infinity, so I have e to the minus minus infinity, so I have e to the infinity, but e to the infinity is infinity. So it looks like I got 1/3 of infinity, which is still infinity. This is not a number, so this integral, what is this guy? X squared. So the integral from negative infinity to infinity of x squared e to the negative x cubed dx diverges because that limit was infinity. These are the cases where if I get an indeterminate form, if I end up with an infinity minus infinity after these limits, I actually can't solve those because they're dealing with different variables and different rates, and I won't be able to resolve those issues. So I just kind of say does not exist for those, or it can't be determined. The second type of improper integral is when there is a problem in the domain. See, this is actually a fairly straightforward problem. I could say u equals e to the x minus 1, du equals e to the x dx, turning this into the integral from, let's see, e to the minus 1. This is 1 over e minus 1 up to e minus 1 of 1 over u du. And I'll say, yeah, okay, alright, I know the antiderivative, that's equal to the natural log of u, and I'd evaluate that from 1 over e minus 1 up to e minus 1, right? Perfect. So this is natural log of e minus 1 minus natural log of 1 over e minus 1. But that's not true. And the reason for that is this is not a continuous function. Right here, if x is equal to 0, which it is, between negative 1 and 1, x does cross 0, then the function divides by 0. One of the conditions of a definite integral is that your function should be bounded on the domain that you're trying to integrate on. So this is an improper integral because it doesn't satisfy one of the conditions of a definite integral. So what we should do, of course, is split the integral and take limits as it goes to the problematic spot. So let's see. The integral from -1 up to 0, b to the x over e to the x minus 1 dx, plus the integral from 0 to 1 of e to the x over e to the x minus 1 dx. And again, since we're doing different integrals, we should be doing different limits. So this is equal to the limit as t goes to 0 minus of the integral from -1 to t, e to the x over e to the x minus 1, plus the limit as r goes to 0 plus the integral from r to 1 of the same thing. Now what? Well, we'll go ahead and do the antiderivative. We already know that there's a u substitution involved. So let's see what we get here. We get t goes to 0 minus our new bounds would be e to the t minus 1 up here, 1 over u du, and 1 over e minus 1 down here, plus the limit as r goes to 0 plus of, e to the r minus 1 all the way up to e minus 1 of 1 over u du. So I've got two problems. I have the natural log of e to the t minus 1 plus, minus natural log of 1 over e minus 1 plus the limit as r goes to 0 plus of the natural log of e minus 1 minus the natural log of e to the r minus 1. Fortunately, I think, nope, not fortunately, very unfortunately, the limit as t goes to 0 minus of, well, we'll just go ahead and apply the limit. If I plug in 0 minus, as t goes to 0 minus, e to the t goes to 1, and which means I have 1 minus 1, which goes to 0. But as natural log goes to 0, it goes to negative infinity. So this is negative infinity minus, well, some number. Plus, what did I get from this other one? I got the natural log of e minus 1, some number, minus, well, I had the same thing here, infinity. Both of these, both are divergent. So what I have to conclude, oh, this is a negative infinity, just being careful. So what I have to conclude is that this limit actually doesn't exist, or this integral. The integral from -1 to 1, e to the x over e to the x minus 1 dx is divergent, because the limits were divergent. I don't get to try to cancel those minus infinities, even though it looks like it would work, but I don't know if they're the same infinity. One of those could be twice as big as the other. I can't really resolve this kind of a situation, so I just say it doesn't work. Sometimes, though, we might have a problem which we won't exactly be able to evaluate the antiderivative of. Or maybe it gives us a limit that's really, really hard. It's not always hopeless. Sometimes there's a way out. And the way out is a comparison test. This is actually a setup for when we get to chapter 11, but there's actually a lot more we can do to compare things. But this one's the easiest to cook up. And I get this from the following exercise. I want to find all values of p for which the integral from 1 to infinity of 1 over x to the p dx converges. I also want to find out when it diverges. So I'm going to try not to think too hard about having a p here. So I'm going to try not to think too hard about having a p here. And I'm just going to try to evaluate this integral. So I'm going to find out, let's see, the integral from, no, that's improper, type 1, so I have to do the limit as t goes to infinity of the integral from 1 to t of 1 over x to the p dx. Now, this will actually change derivatives based on, not derivatives, but antiderivatives. This integral will change based on how big p is. So, if p is not equal to 1, actually I'll do p equal to negative 1 down here. That's what I wanted to say. If p is equal to negative 1, I'm going to have the limit as t goes to infinity. Sorry, it's already on the bottom. If p is equal to 1, 1 over t, 1 over x dx. This gives me the antiderivative of the natural log of the absolute value of x. And I'm going to evaluate this from 1 to t, but that's equal to the limit as t goes to infinity of the natural log of t, well, minus the natural log of 1, which is just 0. But this limit is still infinity. So this diverges. So let's try p not equal to 1. If p is not equal to 1, then this antiderivative is going to use the power rule. So this would be equal to the limit as t goes to infinity. That's x to the minus p power. So this is x to the minus p plus 1 divided by minus p plus 1. And that's evaluated from 1 to t. So I have t to the minus p plus 1 all over minus p plus 1. Minus 1 to the minus p plus, well, 1 over minus p plus 1. So let's see here. T goes to infinity. I actually know a couple of things about this. So t is going to infinity. So if p is bigger than 1, actually, no, let's say this. If p is equal to 1, well, it doesn't work because I'd be down over to the right. So if p is bigger than 1, then minus p plus 1 is less than 0. This would be the same thing as if I just subtracted p from both sides from up there. But if the exponent here of this guy is less than 0, that means this limit, or t to the minus p plus 1, becomes 1 over something that goes to infinity, because I have very big numbers with negative exponents, which means that goes to 0. So I get equal to minus 1 over minus p plus 1, which is a number, converges. Now if p is less than 1, then minus p plus 1 is greater than 0, which means t to the minus p plus 1 is something that looks like something that just goes off towards infinity with an exponent on top of it. And so I'll get infinity, which diverges. So to answer the original question, the integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1, any number greater than 1, no matter how small, and it diverges if p is less than or equal to 1. And this is kind of our target basis for the comparison theorem. Specifically, we call this the p-test. So the comparison theorem says A, if f of x is greater than or equal to g of x, and they're positive, then if the integral of f of x converges, so must the integral of g of x converge. This is kind of like a squeeze theorem for infinite integrals. F of x is a function which is bigger than g, and it's positive, but the integral from a to infinity converges. I do this limit stuff and I get a number, but g is a smaller function, so when I find out whatever this number is, it must be a smaller number, or possibly the same number. The point is it'll be finite. And b, if the integral from a to infinity of g of x diverges, basically the smaller function is divergent, then so must the integral from a to infinity of f of x dx diverge. And how do we use something like this? Well, it can vary from problem to problem. Well, let's suppose I had the integral from 1 to infinity. That has a really nice integral symbol. Of cosine squared of x all over 1 plus x squared dx. Notice that this function is positive. So that's a big checkaroo. I'm looking at it, and what I see on the denominator here is an x squared. So I want to try to compare it with one of these p integrals. I want to try to do the p-test. But the problem is I've got this extra cosine, I've got a 1 here. It doesn't match up exactly with 1 over x squared. So since I've got an x squared on the bottom, I would like to compare it to 1 over x squared. But 1 over x squared, that's a p greater than 0, which means it's convergent. So what I want to do is I want to try to find a bigger integral which converges. So I'm going to look at my function and see what I can make bigger about it. Well, cosine by itself is always between -1 and 1. So this is going to be less than the integral from 1 to infinity. If I replace the cosine with 1, which is bigger most of the time than cosine, of 1 over 1 plus x squared. So I'm getting a lot closer. Now let's see if we can do it again. If I remove this 1, my denominator will become smaller. Let's try this. 1 over 3 and 1/2. If my denominator becomes smaller, I actually got a bigger number. So here, if I remove the 1, I end up with a bigger function again. But I know what this does. This is a p greater, or let me say that, p equal to 2, which is greater than 1. So this is a convergent integral. But my original problem was smaller than this integral, so by comparison, to my p integral, 1 over x squared dx, comma, the integral from 1 to infinity of cosine squared of x all over 1 plus x squared dx must also converge. We'll notice here, We'll notice here that I didn't actually find out what any of these converged to. I just knew, but from the test, that the integral I ended up with was convergent, and it was bigger than my original, so it must also converge to something. We just don't have any way of finding out what. Arguably, we could go back to the previous section and try to use some of those numerical approximation techniques to try to find out what the number is. But the comparison theorem really goes both ways, and it doesn't always have to be compared with one of the p-test types. It could just be compared with any integral you've already found to be convergent or divergent.